Today is multiple regression. In simple linear regression, we got one y and one x. That's why it's called simple. It's a straight line in 2 dimensions. Multiple regression, we have more than one x. And we can have as many x's as we want. This is what they do when they do assessments for property. Property assessments, property taxes. It's how big is the lot? How many bedrooms does the house have? How many bathrooms does it have? How many floors? How many square feet? So that there's 4 or 5 different things that go into predicting the value. So that it's a way to do the same thing except in multiple dimensions. The problem is you can't envision it. If it's x and y, we can make a picture. If it's x, y, and z, we can make a picture, draw a graph, but it's harder to interpret. When you get to 4 dimensions, you're out of business. So that everything about the linearity and the spread and all the rest of it is exactly the same in the assumptions, but you can't check them. You can't see it. So that it's more difficult to handle theoretically or practically. It's no more difficult to do because Excel handles this just no problem whatsoever. Look at the My Open Math, and there's blood pressure data. And this is still in a comma-separated file. Excel has restrictions on what it will do with comma-separated files, but only if you save them or try to save them as a CSV. And it says right off the bat, some features might be lost if you save this workbook. This is blood pressure by age and weight. This is the systolic blood pressure. And we're going to do the scatter plot for blood pressure by age and blood pressure by weight. This is the only thing that we can really check for our assumptions. So insert, charts, scatter plot, and since I was in that data, it automatically did age and weight and blood pressure. You can do it regular as the insert, charts, scatter plot. Excel tries to do a lot of things for you, and sometimes it's helpful and sometimes it's not. Select data, add. First one is age. That's the X, and the Y is blood pressure. So we get blood pressure by age, and it looks like a pretty good straight line. Blood pressure by weight. Charts, right-click, select data, add the X now is weight, and blood pressure is Y. So we've got 2 straight lines in age and weight. What we don't know is how age and weight are related, so that there's a dimension of this that we can't check. We can add a variable. I'm going to add a variable, age times weight, so that I have some handle on how age and weight change together. And if I graph it by age and weight, I can look at it at least. But this is age and weight, so that age and weight are correlated. So when I make this regression by age and weight, it's got another layer in it that I might have to deal with. So I'm going to make a variable, age, and this is purely to handle what age and weight might be doing together. So it's equal age times weight. And it has no justification other than I'm trying to see in 3 dimensions what I can't see in 2 dimensions. So I'm going to try and let the regression handle this. The Excel will do this. The problem is that the Y variable has to be in one column, and the X's, all of the X's have to be in the others, and they have to be next to each other. So I'm going to have blood pressure is equal to an intercept plus B1 times age plus B2 times weight plus B3 of age times weight. The B0 is what it would be if age is 0, weight is 0, and age times weight is 0. So the intercept is just a place where nothing happens. This slope goes with age. This slope goes with weight, and this slope goes with age times weight. Otherwise, it's exactly the same. So if I wanted to get the equation and then predict with it, I put in an age times weight, multiply it times that. Weight, multiply it times that. Age, multiply it times that. Add the intercept, and I get a value out. So it's the same linear equation, and it can only handle linear, although the variables don't have to be just regular. They can be age times weight. They can be age squared, log height reciprocal of age kind of thing. So now, this is how this goes. And you need the data analysis ToolPak. If you haven't got the data analysis ToolPak, it's File, Options, and this one, the screen resolution, has a More, Options, Add-ins, Excel add-ins, and this shows you what's already in there. This data analysis ToolPak is already in here. But if it isn't, go to Excel add-ins and go and check data analysis ToolPak. So I've already got it. And we want regression. This is exactly the same function as we used for the 2 variable, the X and the Y. Input the Y range. And we're going to include the titles, or the column titles. But then the X range has to be all together. I can only mark it as one block. I can't have any gaps. All the columns have to be next to each other with nothing in between them. And I've got the titles as well. You have to click labels because we've got the labels in the first row. The age times weight, and so on. Output range is exactly the same. We just pick a spot. And I always like to put them on the same page so I know which are associated. Look at the rest of the stuff down here. In particular, down in this spot, it says residuals. This is the only way that I can check to see whether the regression assumptions are met. And it really is pretty lousy. The residuals are the mistakes. This is what we did with the other regressions where we had the observed minus predicted. This is the same thing, observed minus predicted, except now we have 3 X's that will predict, and we want to click residuals. There's also in here normal probability plots. Most of this stuff is crap. It's useless because you can't see it very well. But the residuals, instead of having to calculate them, it will calculate them for you. And it's going to just put them all in a big string. Make sure labels is marked, output range is something handy, and residuals is checked. You can do this with the simple linear regression too, but it's not as much use. Click OK. And it spits out everything you need. And get the charts out of the way. Up at the top it says R squared. This is the coefficient of determination. It's the amount of variance in blood pressure associated with age and weight, and age times weight. The multiple R is the square root of that, and that means nothing. It didn't mean anything in the simple linear regression. All it is here is the square root of the R squared. And this is something that the Excel people who wrote it just threw in because somebody said we need to have a correlation coefficient. The R squared is the only useful thing. If you want the square root of it, there it is. The adjusted R square. Now we have 3 X's. And the adjusted R square takes into account the number of X's. The fact is, if I add variables, I can make the R square go up. I can make the regression look better. The more variables I have, the higher the R square will be, although they may have nothing to do with it. I can put in random numbers here. We'll do this later. So the adjusted R square is an attempt to look at the influence of the number of variables. Basically, it's not much use, but that's what it's trying to do. And there's better ways to do this than that adjusted R square says. Down in the ANOVA portion, that sum of squares, here it's 42.5. This is the residual sum of squares. This is what we want to minimize both in the simple linear regression and in the multiple regression. And there it is. It's calculated for you. We don't have to calculate it. Down in this part, this is all of the information that we need from the regression. And I'm going to cut it at 3 decimals. We don't need all the decimals. But here in the coefficient column, the intercept is 11.34. So that this says blood pressure is equal to 11.34 plus the slope for age is 1.144. 1.144 times age. That means for every year of age, the blood pressure goes up by 1. It's still slope, rise over run, blood pressure by age. The next one is the weight, 0.445. For every pound change in weight, the blood pressure goes up. Rise over run, it's blood pressure by weight, so that both of these are positive. The blood pressure is going up with age and weight. The older and the heavier, the higher the blood pressure. The last one is this variable I made up and threw in there, and it is minus 0.002. So that's got to go. Minus 0.002 age times weight. That means as age times weight goes up, the blood pressure goes down. It's negative, so that the slope associated with age times weight, that variable I put in to try and handle the interaction of age and weight, is negative. So that's the equation that we would use to predict. Pick an age and a weight and stick it in that equation and you get a predicted blood pressure. Look at the other columns. This column is the standard error column. And unless you are going to do the test statistics to calculate something, you don't need it. Here's the part that you need, the T statistic. Anything bigger than 2, basically, is important or significant at the 0.05 level. Look at the intercept. What's the T statistic? Is it anywhere near 2? It's not significant, and you can look at the p-value. This is the actual significance level. And if it were 0.05 or less, it would be important. It's 0.161. The p-value is 0.877. It's nowhere near a tail. The age, 1.11. P-value of 0.3. Weight, same thing. Basically, nothing in this regression is important to predicting blood pressure. Do you believe that? That age and weight have nothing to do with blood pressure? No, not a chance. Age and weight have got to affect blood pressure. Something is screwed up. Now you get the difference between statistics and what's real. I ran this thing and I got squat. So I am perfectly justified in saying age and weight have nothing to do with blood pressure. Although that makes no sense. So I have to look at what is going on. What am I doing that could cause this thing to go sideways? And in this case, it's the age times the weight. And the way I can check that is to get rid of age times weight as a variable in there. Age and weight, I think, should have something to do with blood pressure, but this doesn't demonstrate it. So I'm going to repeat this without the age times weight. One other thing before we do that, I'm going to blitz these graphs. I don't need them. Look at the residuals. Here is the predicted blood pressure, and the residuals is how much I missed by. And there's one for each of these. This is as if I went to a column here and got the predicted blood pressure and did the residual, the observed minus expected. But if I graph these things, predicted blood pressure versus the residual, insert, and I got it marked so that I'll get blood pressure is X, residual is Y, and I make a graph. What I'm looking for here is the association between the predicted value and the residual. Is there any pattern in that graph? See a line in there? There's nothing there. This goes along with the result I got from the regression. But this is the only way I have to check whether the assumptions are fulfilled for the regression. And basically it says, I got crap. I'm going to blitz that. I'm going to erase the residual output since I don't need it. Home. Get rid of the lines, no borders. And I'm going to repeat the regression, except I'm going to use only age and weight. So I'm going to put it down here below this, and it's the same as before. Data, data analysis, and regression. When I do this, in this version of Excel, all of those variables are still in there. So unless I change something, it's going to overwrite my results because the output range doesn't change, and I'll get the same X and Y. So I want to change the X's. The Y range is good. It's blood pressure. Instead of age, weight, and age times weight, I want age and weight. And I'm going to put it down here, somewhere where it won't write over my previous results. I'll still get the residuals, but now I've got two variables. Look at the R square, 0.988. Before, it was 0.98848, 0.98835. It was slightly higher before because I had three variables instead of two. 0.976, excuse me, I was looking at the multiple R. 0.9768, 0.977. So it's a little higher with all those variables in it. But here is the important part. Look at the T statistics. The T statistic now for the intercept, the B0, is now 2.59. It is significant. 0.03 is less than 0.05. Look for the 2. For age, it's now 3.47. It's significant, and weight is significant as well. So I threw in a variable that wasn't justified. It could have been important. I had to check it. If I had stopped here With this, with the age times weight in it, I would have nothing, and statistically, I am entirely justified in saying age and weight do not affect regression. All right, you want to lie with statistics, throw in another variable that's got nothing to do with the results. A random number. And you can wash out any effect if you have enough crap. You put enough crap into it, you will remove statistical significance, and you will see this in results. This is why you see things on the news that say, this has nothing to do with anything else. Or it does have something to do with it because I've forced it. I can manipulate the numbers by adding variables. If I add enough crap, I can get the result I want. Statistics is one thing, reality is another, and this is one of the results. Here, age and weight are highly connected with blood pressure. And if I put this in, every year of age raises blood pressure by 0.86. Every pound of weight raises blood pressure by 0.33. And if age and weight are left at 0, the blood pressure is at 30.99. If you had a blood pressure of 31, what would be your physical condition? You would be dead. All right, it's significant, doesn't mean anything. All it is holding a line down. Go back here, and I'm going to add a column. Insert a column. I'm going to keep age and weight in here, but now I'm going to add a random number. And I'm going to call it random number. And for this, I want equals rand, R-A-N-D, between. There's the rand between command. And I want to add a random number between 45 to 75. It's just a range. And I got 58. Did you put in rand between? Would you get a number? You get a different number? Probably, because they're random numbers. And I'm just going to copy it down. This time, I'm going to run the regression on blood pressure with age, weight, age times weight, and a completely random number. And I want to see what happens with the R-square and with the coefficients, which ones are significant. But the setup is the same. Data, data analysis, regression. I have the Y variable, blood pressure. I want the X variables now to be age, weight, age times weight, and a random number. Labels are good. The output range I have to change because it'll write over my other results. And I'm not going to screw with the residuals. What the heck? And click OK. And I get, and you'll have slightly different results because you have different random numbers. How does it look? Are the age and weight important? Look at the T statistics for this thing. Is anything there significant? Not a thing. Look what happened to the R-square. Here I got 0.977. When I did it the first time, I got 0.9 771. This time I got 0.9772. The R-square went up. This is where the adjusted R-square actually has a use, because I tossed in a trash variable. The R-square with age and weight was 0.976. I raised it to 0.977. If I'm solely going on R-square, I have an improvement. I gained something. What I actually have is trash. But by adding a variable that has nothing to do with it, I raised the R-square. And for some people, the R-square is the only criteria they're interested in. They want the highest R-square possible. If I add another 5 random number columns, I will increase the R-square again, so that the common criteria of R-square, how much variation is soaked up by my dependent variables, is open to manipulation by adding variables that have nothing to do with it. All the stuff I got statistically is good, and it's completely open to manipulation. Close this one out. We don't need this anymore. Go to the edited health data. And the original data set had 1,000 observations or something. I've cut it way down. But I want to predict blood pressure, systolic or diastolic, from the variables I have here. I want to use age, gender, height, cholesterol, weight, smoker, diabetes, and health. The way it's set up, I can't use it because the X's all have to be together. Copy all of that. I'll do it the easy way. Copy the systolic and diastolic columns. And there's 299 observations. Home, copy, make a new sheet. We need to add a sheet and paste those columns. The only reason I'm doing this is because I have to set it up so that I can use the regression command. So now I have what I want for the Y variables all by themselves in the first column, first 2 columns, and then I want all the other variables in the next columns. I'm going to copy the whole thing because I can get rid of columns as easily as I can copy them. So I've got all of it marked. Copy. Go back to the second sheet. Go next to what we have already and paste. I've got 2 columns now for blood pressure. I'm going to delete those 2 columns because they're in the way, and I need all the ones I want as X's all in a block. So now let's do systolic blood pressure versus gender, age, cholesterol, height, weight, body mass index, smoker, diabetes, and health. I want all of those variables, and it's the same as before. Data, data analysis, regression, and I get a fresh start. I want input Y range. I want to predict systolic blood pressure. Then I want the input range for the X's. That's all the variables from gender over. And you just mark all of them, including the column titles, because we're going to put the titles in there. So I've got blood pressure for the Y's, everything else for the X's, because they have to be in a block. Click the labels and make the output range something convenient. And click OK. Here's the results. Look at the R-square. This is the kind of R-square you get when you deal with something with people. 0.51, this is a very good R-square for this. What variables are important in this setup? Here's the coefficients in a column. Gender has a negative correlation with blood pressure. Age has a positive correlation. Cholesterol, height, weight, body mass index, smoker, diabetic, and health have a negative correlation. The slope is negative. Which ones are important? Look at the T statistic column. Is the intercept T statistic bigger than 2? It's significant, and it got a p-value of 0.001. Gender, minus 0.48. It is significant, so that gender is important to predict the systolic blood pressure. Age, the t-value is 14, is extremely important. Is anything else significant? All you're looking for is 2. If you remember nothing but 2 and minus 2, that's all you'll ever need in statistics for significant value. So that basically I could do this without any of those other variables and still be ahead of the game. And in fact, if we do that, we're just going to leave off everything but gender and age. Same setup, data analysis, regression. Everything is marked. The Y variable is marked. The X now, I need to reduce it to gender and age. Nothing else was significant. I'm going to put it further down so it doesn't step on my previous results. And click OK. What happened to the R-square? 0.50 versus 0.51. Because I had more variables, the R-square is higher even if they had nothing to do with it. T statistic now for the intercept is 95. That's significant. Minus 5 for gender and 16 for age. What does the gender sign mean? Male and female. Look up at the top. Which one is male, which one is female? And it's on the other sheet. Smoker. Gender. Female is 1, male is 0. What does that say about gender and systolic blood pressure? It's negative, and that means the 1, female, has a negative relation with blood pressure,